Hi, everybody. I have construction again today, so just annoying noises, and I hope it's not that hard to like hear me, but we'll try our best. Yeah. Welcome. Oops. We're in pre-calculus. Pre-calculus. Okay, somebody was in the wrong class. Okay. We're just letting a bunch of us in. Awesome. Welcome, everybody. October 26th, and we got some patient built in today. All right, let's check it out. Okay. So, our attendance check question is what's your favorite breakfast cereal? And like, it's okay if you don't eat breakfast, but like what's the cereal you would eat even if you don't eat it at breakfast? What's your favorite like cereal brand, type, things like that? All right, let's see. Ooh, Honey Bunches of Oats, Reese's Puff, Fruity Pebbles and Frosted Flakes, Lucky Charms, Cheerios, Chocolate Rice Krispies, Special K. It's the only one that doesn't taste nasty. That Special K looks good. I've seen no, and then Kicks. Yeah, I for some reason got, I don't know. My mom used to get like those healthy cereals when I was younger. She also had Week or Wick, I think it's actually called. My mom would say Week, but they would get like Kicks and stuff, and I would like them. Fruit Loops, Cinnamon Toast Crunch, Corn Flakes. Yep, me. I like that with bananas on top. Fruity Pebbles, Special K with strawberries, Cinnamon Toast Crunch, Frosted Flakes. All right, y'all got a lot of great cereals. Honey Bunches of Oats. A lot of Special K mentions. Someone said Dust Bunnies. Who said Dust Bunnies? Life cereal and Fruit Loops. Wow. Y'all know your favorite cereal brands. Let's see. Let me go ahead and see who we have here and who we don't. Again, I apologize. We're going to have some construction noises. Okay, so this is who I don't have. I don't have Tyree. I don't have Dennis. I don't have Alicia and Marco. So that's who I don't have. That's about four of us. If you're friends with them, um, please let them know. Send them a text so that they can come into class and get some of their points. Participation is what we're gonna get. Let's not. I want to try chocolate Lucky Charms. Yeah, let's be nice about people's different cereal preferences, y'all. Thank you so much, everyone, for participating, though. Okay, let's move on. All right, y'all. So this is what we're going to be doing for attendance check. Sorry, for our agenda. We did our attendance. We're going to have some notes today that you definitely want to pay attention to because you're going to have a Google form participation check after that. And it's going to be based on the notes that we take today. So definitely pay attention. And yes, you want some paper, you want pencil, or if you're doing digital notes, have those ready. Then, after we do a process check on something called a left Riemann sum, we're going to talk about something called a right Riemann sum. After that, then we have our checkout. Asynchronous number 12 was posted, but that one's due Tuesday at midnight. So that's our general agenda. And yeah, let me know if anyone has any questions about async work or anything. I just know I was very happy. I had a lot of students come in during today's office hours. I was really really busy, but it brings me a lot of joy, to be able to help. So feel free to jump in the office hours if you need any help with any of the asynchronous work. I'm happy to help you with it. All right, so let's go. Let's get your notes ready. Oh, we got Tyree. Yay! Fix up my attendance here. Welcome, welcome. Awesome. Okay, let's go, y'all. So before we get into notes, so again, you should have your notes out and ready, or if you're taking, yeah, and I remember that that's you, August, because last week, yeah, I got you. Don't worry. All right, so last week's recap, everybody. So we're gonna do a recap on last week. So last week I took screenshots of the work we did in our groups, and also what the essential question was and what the learning target was. So the original question was, I can investigate how to approximate area under a function and also interpret the meaning. That investigation is shown right here. I took some screenshots of some great, really great posters. As you could see, the different methods that each group did. And the learning target we didn't hit. The learning target we didn't really get to hit was I can explain how to approximate area under a function using Riemann sums. So the learning target from last week, we didn't really hit, but that's what we're going to hit today, and also perhaps some of the next lesson as well. All right, so let me know if, again, that's the recap, and I'm updating the attendance for those that just came in. Welcome, welcome. So happy y'all are here. Okay. So yeah. Okay, next up. The super important thing though that you should have got from that activity was how to determine the units under a rates graph. Now the graph you all worked on last week with your group was a beats per minute graph. So this right here was a beats per minute graph, and I explained to you that this connected to our big idea because the area under a rate graph represents total accumulation. And when you do rate times time, that gives you the accumulated unit. In this case, the y-axis represented beats per minute, so you wrote it as beats per min. The per means divide, so that's why beats per minute is there. You multiply by the time, which is, in this case, what your x-axis units are, which is minutes. Those cancel out, and you get that the accumulated unit represented the total beats. So in this case, Bristol, the area under the curve represented the total heartbeats that Bristol made in that time, which was about 10,000, like over 10,000 beats that her heart had made. It's not beats per minute that her heart made, it's total beats that her heart made. So that's important to distinguish. And as you all saw, you approximated the area under a curve with various different methods. And I was super happy to see the different methods y'all came up with. But the method that we're going to talk about today is called the Riemann sum method. I kind of talked a little bit about it last week, but we're going to finally talk about it now. So again, this was a recap from last week. You don't have to copy this down. But here's the learning target. Let's write this down in our notes now. So now we're going to focus on this learning target. The title of today's notes is Estimating Area Under a Function. The learning target is I can explain how to approximate area under a function using Riemann sums. So let's write that down, and I'm going to mute myself because I know there's construction noises. A few more seconds to just write this down in your notes. All right. I hope you all got down this learning target with our title. Again, it's kind of like from last week. So I hope you also got it down from there. But if not, the slides are on Google Classroom. Let's go ahead and get these notes in motion. All right, so I talked briefly about this, and you could go ahead and do like brief notes. You don't have to write down this whole thing, but just so you know, what is Riemann and where does that name come from? Why does it sound weird? So again, Riemann is the last name of the man who used this approximation method, and his method is basically drawing different kinds of rectangles under a curve to approximate their areas. And usually, the curves he was looking at was rate curves. So in physics and things like that was where the connection was made. So if you had like a certain velocity curve, they were very interested in determining, well, if I have this velocity, how far did I travel? What was my distance? That's when you would use area under the curve to figure that out. Um, and again, we use his method, the drawing rectangles under a curve, because it actually in calculus, you're gonna use these rectangles to find the precise area under a curve. As you could see in the visual though, the more rectangles you draw, the more thinner their widths are, the better your approximation. So that's just a visual for you there to see how this method can actually get you a really precise area under curve measurement when you do more rectangles. Let me just pause on this slide so y'all can get this down. All right, so I hope you just at least got the bullet points. You don't necessarily need to draw like the rectangles and so forth. That's just for your visual and like just so you could see that the more rectangles we use, the better. And of course, when you use more rectangles, the more calculations you got to do though, right? It's more work when you do more. The approximation gets better, you got to do more calculations. So that's a little background. Um, yeah, and that's kind of what it verbally said there. The more rectangles you draw, the better the approximation. Okay, y'all. So the first Riemann sum that we're going to take a look at is called a left endpoint rectangle. So we're going to talk about what the left endpoint means in a second. But first off, here's the visual. So first, let's copy this down. Let me give you a minute to copy this down. I do want you to know that when you copy this down, it might look a little off because let me show you. For example, 2 hits at 1 right here. But when right here at 1.5 up to here, you have to be careful because that doesn't hit at 2. The height of that rectangle is a little above the 2. So be careful when you're doing your sketch here. This does hit perfectly at 4. This one's going to be a little bit above 6. So yeah, be careful when you're doing your sketch. But let me give you some time to sketch this first, and then I'm going to talk about what this represents, what this means, why is it a left endpoint rectangle. Please pay attention at this portion though, because we're going to have our Google form on this part. So let me give you a minute to sketch this down. All right. I hope you got the sketch of the rectangles. Again, I drew these lines so you could see that some of the rectangles' heights are a little bit above a whole number. So just be careful when you're doing your sketch. Let me just clear those lines though, because they're not actually not part of your graph. They were there just to see help you see the heights of those. Okay, let's get down these bullets. First thing you should know, again, one way to estimate the area under a curvy graph is to draw rectangles. And that's the method that we're going to continue to investigate. Some of you actually did use rectangles when you did the Padlet too. In the visual right here to the right, we're using rectangles to estimate the area under the function f of x equals x squared. So this here is the function f of x equals x squared. And we're trying to figure out its area using rectangles from x equals 1 to x equals 3. So the area that we're interested in is, so this is where x is, ooh. As you all are writing down that bullet point, I'll just kind of do this for the visual. Like, so we're doing this area from 1 to 3. And that includes basically this whole area of like if I was to like color this whole thing yellow like this, that would be the whole area we're actually interested in. But you don't have to do this. This is just so you can visually see. We're trying to estimate this whole yellow chunk, the area under the curve, and it stops once it hits the x-axis. And we're using these rectangles to do that estimate, right? Let me just undo the colors. Yeah. So just so you know, these rectangles are trying to do an approximation of that yellow area that I just showed. Let's see if there's a comment there. Yeah, Francisco, you put the triangles. Yeah, so it's not perfect because those triangles are not accounted for. So if you really wanted the true area under this here function, you would want to try to like figure out the area of those little triangles that weren't accounted for. Yes. Okay. Next, though, in order to be more precise of our function heights, we have to use the function to determine the height of the rectangle. So I'm going to show you how to do that in the next slide when we actually work this out. So we'll talk about this bullet in the next slide. I want you all to notice that in this visual right here, the base, basically the base width of each rectangle down here at the bottom. So the width of each rectangle is the same. And each width is 0.5. Notice how it's like 1, then it goes to 1.5, then 2, 2.5, then 3. So basically the width of each rectangle is 0.5, and it's the same for all of them. They're all have the same width, but their heights are going to be different when you're calculating the area of each rectangle. So that's just something to notice. And lastly, why in the world are these called left endpoint rectangles? Yes, and then yes, Francisco, all the rectangles have the same base. Now these are called left endpoint rectangle. Notice how the upper left-hand corner of the rectangle is touching our graph. The graph is right here in black. It's this curve. This is our graph, f of x equals x squared. This is a parabola, but we're only looking at the positive half of this parabola. And notice that the upper left-hand corner, let me change my color in red. This is the upper left-hand corner of each rectangle is touching my graph. Notice how that's the case. That's why these are called left endpoint rectangles, because the upper left-hand corner is touching your graph. So that's the reasoning for their name. After your Google form exit ticket, we're going to talk about what the right endpoint rectangles look like. All right, let me have a few more seconds on this slide. And then we're going to talk about the actual process on how we calculate and what we need in order to do the calculations. I think the next slide is actually what we need, and then we're going to do it. And then we're going to have a Google form to have you like analyze like what you understood from it. So it's going to be a process. All right, awesome. Let me clear this up. And then let's move on. Again, the slides are on Google Classroom in case you're missing a bullet or something. All right, so what do we need to do our calculations first off? So this is just something so that you have some notes on like, okay, this is what I need before I do my calculations, before I calculate the thing called Riemann sums that we're about to do. First thing you need, rectangle widths. As you noticed, I pointed it out in the last one. We all saw that the widths were the same, 0.5 units. And usually with Riemann sums, they're all always the same. Number two, we need the rectangle heights. So we need the heights in order to find the area of each individual rectangle, because the area of a rectangle is base times height. In our Riemann sums, the height is always going to be the y value, or the y value of our function. It's always going to be the case. Super important. Then we need to remember that once we find the individual areas of each rectangles, we need to add them up. We need to sum them up for our approximation. Then the other thing we need to remember is the units, if there are any. So sometimes there's no units. In this case, there aren't no units. So sometimes you're going to be given a general function and you're going to be asked to try to approximate the area. Sometimes you don't have units, and in our problem right now we're not having units. So for example, it's not going to be beats per min. We're not actually looking at units for this problem, but if there are units, you want to make sure you pay attention to them. Last thing that we need to keep in mind for this process is we're going to be using subscript notation to organize the endpoints for segments on the x-axis. So for those who don't know what subscript notation looks like, it's, for example, if I have like x and then I do sub 0. That's x sub 0. It's like a subscript 0. Or I could do x sub 1, the little 1 right here. So this is just like subscript notation is used to kind of organize data, and that's what we're going to be using in the next slide. So again, that's subscript notation. That's for this bullet. You'll see it's not going to be too bad. It's just as a way to count. Is what we're going to be using it for. All right, we're going to have a few more seconds on this slide. All right, y'all ready for our how to do Riemann sums? Let's try this out. So again, we're doing this with a basic example. Then we're gonna be like throughout, in these days coming up, we're gonna try to be more precise. And how we be more precise is when you draw more rectangles. Again, remember what that means is more calculations. Got to be careful when that happens. But right now, let's start with this. And again, we're gonna have our Google form exit ticket based on what I'm doing right here, right now. So definitely ask questions if you have them. So here what I have for you is, again, the same graph. We have these left endpoint rectangles. But what you notice is at the bottom of them, I added subscript notation. These subscripts are helping us identify the endpoints of the segments in our graph. What does that mean? So for example, x sub 0 corresponds to 1. 1.5 corresponds to x sub 1. 2 corresponds to x sub 2. 2.5 is corresponding to x sub 3. And the last number 3 is corresponding to x sub 5. So we want to start by labeling, our endpoints of the segments. And these are the endpoints of them. It's just a practice that we're going to continue to do. Cool. Okay, let's do the first rectangle. I'm going to color code it for you. Take a look. It's in green. I know it's a little crooked, but it's supposed to represent the first rectangle. We're going to try to find the area of that. Before we start, I do need the height of the rectangle. We all already know that the width is 0.5 of each of these, but I need the height of this rectangle. How we find the height is sometimes it's easy to see in your graph or if you have Desmos. For this one, I'm going to show you that we're going to be using our, let's see the chat. Okay, that was just private chat. Okay, for this one, in order to find the height, we need our function. Super important. That's why I have the function written up here. The function that we're given is f of x equals x squared. So in order to find the height, we're going to do this calculation right here. Notice how I plugged in my x sub 0 number, which was 1. I plugged in 1 into the function. So 1 squared is 1. 1 squared is 1 times 1. It does not mean 1 times 2. My output is 1. So when you go back to your this here upper left-hand corner, you're going to label that as 1 comma 1 because my output was 1. Yes, you could see it visually in the graph, but you're going to see why you need your function to find the rest of the heights. This one was a basic example. Okay, now that we have the height is 1, the base is 0.5, we have everything we need to find the area of this first part in green there. And here's the first area, base 0.5 times height of that rectangle is 1. So the first area is 0.5, and I put units squared because we don't have any units. I put units squared because squared usually represents area. So that's the first one. Let me just pause here, see if anyone has any questions so far on what we're doing in our process. Okay, cool. Let's continue to follow along. Again, remember, pay very attention because in our Google Form exit ticket, I have a screenshot of this very slide, and I'm going to circle parts. I'm going to ask you to explain what am I doing and why. So be careful there. Okay, next one. Now let's move on to the next rectangle we have. And this one, I color coded as red. All right, I know that the base is 0.5, but I need the height. And remember, I pointed out before that the height is not 2, even though it looks like it's at 2. You got to be careful. And I wish I could do a dotted line, but the height is like a little bit above 2. See, it's like 2 point something. You don't want to make an estimate here. What you want to do is use your function to find the height. That's why I'm going to do my work up here. So let me go ahead and clear. Let me undo that line. Let me show you. So the next point that we're going to plug in is x sub 1. X sub 1 is 1.5, right? Because this is 1, this is 1.5. So the number I want to plug into my function now is 1.5. See that? When I plug in 1.5 squared, that's going to be 1.5 times 1.5. That's going to give me the y value of 2.25. So that's the actual height of this red rectangle. So you're going to label this point as 1.5 comma 2.25. See how the y value is giving us our heights. The y value is the height of the rectangle. Now that we have the height, we're going to do base times height. So the base is 0.5. My height is 2.25. Let's go to the side again. In red, you're going to see that. This is what I got as the area of the red rectangle. Yeah, so for that one, you wanted to make sure you're careful. So you want to be precise, and you want to do oh, and then a question I was asked is, do we have to do the multiplication with the parentheses like I'm doing, or can I do the X symbol? You could do the X symbol if you want. So if you're more comfortable using like an X symbol to multiply, you could do that. Totally means the same thing. Cool. So let me pause here to see if anyone has any questions about the 2.25, right? Like, how did I get that height? Again, remember, I used my function that was given to me. I plugged in this, the x sub 1 value, which is at 1.5 right here, to get me my height, which is 2.25. Once I had my height, I was able to multiply to the base of the rectangle and find the area of that rectangle. Again, remember, area base times height. All right, let's keep going then. The next rectangle I'm going to color code as blue. And for this one, the one we're going to plug in is x sub 2, the subscript, and the number here is going to be 2. So we plug in 2 into our function that's given to us. The input is 2. Square it, that gives you 4. 2 times 2 is 4. So then my coordinate point is going to be 2, comma 4. Again, here's my input is 2. My output was 4. Let's see what's in the... Yes, I have a great clarifying question there in the chat. Someone asked, and this was a private thing, so you always use the function given to find the height? Yes, you use the function given to find the height. That's correct. Let me also write that down as a note, because you might want to say that in your exit ticket. You use the function given to find the rectangle heights. Super important. So that's why I keep kind of going back and showing you that I'm using my function. And I'm using a basic example like f of x equals x squared to show you this. So now let's go ahead and find the area of this blue rectangle. So again, base is 0.5. My height is 4. So I'm going to do 0.5 times 4, which is going to be just 2 units squared. And I wish I could kind of just show you all how, yeah, I wish I could put like 0.5 times 1, you know, how the calculations are going. And then this is 0.5 times 2.25. Hard to see anyway, but just notice that the y values are my heights always, and you use your function to find those. And it's going to be 0.5 times 4. Okay, cool. Let's do the last rectangle. Last rectangle is going to be color coded in purple. It's gonna be our last estimate. So you notice, y'all, if you did more little baby rectangles to get a better approximation, it's gonna be more work, more calculations. So for this rectangle, we're gonna be using the input x sub 3, because that's the next one that gives our height of the function right here. See, it's gonna be this one. It's not gonna be x sub 5, because that's over there. We have to look at the one that's touching the upper left-hand corner that's touching the graph. So this is going to be the input of 2.5 here. So we're going to plug in 2.5 into my function to get the precise height. 2.5 squared, that's 2.5 times 2.5. That's going to give us 6.25 as the y value here. So it's 2.5 comma 6.25. So again, to find the area, you're going to multiply the base, which is 0.5, times our height that we just found. It's the y value, 6.25. Again, super important to obtain those y values. And then if we go off to the side, what do we get? If I do 0.5 times 6.25, we get 3.125 units squared. Yay, so we calculated all the area of these individual rectangles. And again, notice how we didn't need to use x sub 5. We didn't need to use it because this is a left endpoint Riemann sum. When we're going to do a right one, you will use it. So you'll see that in a second after the Google form. But let's go ahead and add them up. Oh, okay. Adding up, Francisco says, oh, sorry, if you wanted that private, but we got 6.75. Let's see if that's what I got. Yeah, 6.75 units squared. That is the area, the total area of those rectangles, and it is also an approximation of the area under this function between 1 and 3. That's also what it also represents. Awesome. So I have one question to ask to everybody in this group, and you could use the chat for this question. Here's the question. The sum that we got here, 6.75 units squared, is the sum greater than or equal to the actual area under the curve? Is this less than, greater than, or equal to the actual area, the actual thing we want to find? If we were to shade this up. Okay, so 2 people said less than. And anyone who thinks less than, can you explain why you know that it's less than? Why? If anyone can type it out and let us.
Because we are missing the triangles.
Perfect. Thank you so much, Francisco. So Francisco said, because we're missing the triangles. Yes, look at these white portions that aren't accounted for. And it was also mentioned, I think, at the beginning, and because it went up to 3, we're also missing this triangle. And then again, because this was the area between 1 and 3, we don't really care about this white part over here. Perfect, yes. The sum is going to be less than because the triangles are not accounted for. Awesome, y'all. Cool. So now, given the notes that we took, I hope you took very precise notes. We're going to be jumping into the Google form, but let me just pause here for like 30 seconds or so, just for those who are still getting this down or still need to process or ask questions. Let me just leave this, and then we're going to move on to the Google form. And it's going to ask you some questions about the notes we just took. All right. All right, I hope you all got this down. Let me go ahead and clear my screen. And then again, if anyone needs the recordings, I'm happy to send it to you. Just let me know. All right, let's go. So this is, again, participation grade. You want to now pause and reflect on the notes we all just took and that you all participated in. And you're going to do this Google form. I'm going to open it up and show you what it looks like as well. We'll have about 10 minutes. Oh, yeah, it is. Thanks, Francisco. I'm really shy, but yeah, my birthday's on the 29th, and I'm going to be 29 on the 29th. Isn't that funny? Yep, days are flying. Yeah, when I started teaching, I was 24. So when I first started at Envision, I was 24. Now I'm 29. That's crazy. But yeah. Okay, let me show you all what the exit ticket looks like and what you're going to be expected to fill out. So this is all about the left Riemann sum. Keep in mind, we still haven't talked about the other one called the right Riemann sum. This is all about the left. The first question you're going to just be asked in your own words, describe the process and purpose of calculating a left Riemann sum. Just in your own words, what do you think? Number 2, you're going to be asked what the portion circled of A represents. So here's A, it's circled. You're going to write down in your own words, what does that represent? What did you understand from this lesson? Number 3, it's going to ask you about what does the portion circled in B represent? What exactly does those calculations I did in the notes represent? For number 4, you're going to be asked about part C. What did that represent? And lastly, you'll be asked about part D that's circled there. So again, this is a screenshot from our notes, and I'd like you to please elaborate and please use because in your explanation and in your sentences. All right, y'all, let's go ahead and have about 10. So basically this is left because we choose the point on the left. That's correct. You choose the left subscript input value. And yes, for the right, you would be using the right, and we'll talk about that. We'll probably just get exposed to it today, but we probably are going to have to formally talk about right remonsums probably in our next class because we only have mostly the time is going to be for this here exit form. All right, y'all. Please make sure you complete this. This is for credit. It's in the chat. Let me know if anyone needs me to share it as well. But we have about 10 minutes and then we're going to come back together. All right, y'all. See you in 10 minutes. Let me know if there's any issues in the private chat. We have about 1 more minute. Make sure that, and by the way, make sure if you do want more time, you could totally submit, like, after our class finishes this, that's fine, if you want more time, but just 1 more minute and we're gonna move on. Alright, everybody, welcome back. Again, if, you wanna use, like, if you wanna turn it in after class, totally fine. I'm gonna be taking a look at, like, what you all said, what are your thoughts, what are you confused on, things like that, like, tomorrow morning. So if you want more time to get this in, you could totally do that. Um, but yeah, so just as a preview for what's going to happen on our next class period, which I believe is Wednesday. No, I think it's tomorrow. I'm not. Yeah, it's tomorrow. Yeah, we'll take a look at the calendar. So our next class period, we're going to take a look at the right endpoint rectangle. Let's take a look at this. See, this is how they look like, and we're again going to be looking at the same graph. Notice how the upper right hand corner of the rectangle is touching the curve. Notice how the upper left-hand corner is now not touching the curve. The one that's directly touching the curve is the upper right-hand corner. So that's what makes this a right endpoint rectangle. We're going to talk a bit about that in our next class period. We'll have our formal notes. So that's just what it looks like for now. Let me X out of here so that we could jump into our checkout. So from what you see, here's our checkout question. So that's the right endpoint rectangle. From what you see visually for now, or what you think, what are the differences between right and left Riemann sums? Just from what you saw right now. Like, I just visually showed you what the right one looks like and what the left one looks like. Um, what are the differences, or what questions do you have? I'm going to also add that here in case, like, to make this more open. What are the differences between, or what questions do you have about today's lesson? That, just leave it open. Again, this is what a right Riemann looks like. You could talk about what are the differences between the two. I know I misspelled questions, but for the sake of time, let's just keep it. um, what are the differences between a right and a left? Or what questions you have about today's lesson as our checkout. Okay, so someone put, wouldn't it be overestimating when they looked at the right Riemann sum? Yeah, it would be actually. So that's a interesting observation. We're going to talk a bit about that. Left Riemann sums gives you an approximate that's less than the actual area, while right Riemann sums gives you an approximate that's greater than the actual area. That's awesome. Awesome difference in similarities. I think the difference is that the left one gives you less, the right one gives you more. How do you know which equation to use to find the height of the rectangles? So usually they're given to you, or sometimes you're gonna have to use like Desmos to figure out the equation. One goes over the line, and then and to if it go one goes over the lines, and that means it's going to be an overestimate. Yes. Left had some area missing, right has some area added. That's good, good insights. The left Riemann sums are determined. It's less than the right Riemann sums gives it greater than the area. Yeah, you're all noticing that, huh? They're different because on the right you go over the line, the left is under. Yes. Those are awesome because those are going to be hitting our next big ideas about approximations and using Riemann sums. And then, ooh, is there any situation where you would need to use both? That's a very good question. And I think we'll answer that as we continue to investigate these and as we hit, into our next mini final. But let's worry about that when that happens. All right, y'all. Those are awesome. Thank you so much for participating. Again, make sure you submit the Google Form exit ticket so that you get your credit. Again, I'm so excited to see what you all put, what you all understand, and I'm so excited to get to talking about the right Riemann sums for next time. All right, everybody. Y'all enjoy your day. Y'all have an hour lunch break. Bye, everybody. Bye. Break.